So let's see, how would we complete this equation? Do you know what does AQ mean?
It's aqueous. It's broken up into ions.
Let's see. In this case, that would be right, but that's not exactly the definition of aqueous. The definition of aqueous just means dissolved in water. So when we see AQ, we're thinking that these things are dissolved in water. Now, what would the products of this reaction look like? Well, the key thing is, you know that there's some elements that when they meet up with each other, they precipitate out. Or I don't know whether you've actually studied that yet in this term, but maybe you've seen before that when two elements meet each other, if they're not soluble, they're going to precipitate out. Now, there's certain elements that are always soluble. For example, sodium plus and potassium plus and nitrate, these are always soluble. They never precipitate out. But other elements, when they meet up, it's possible that they could precipitate out. And of course, what you want to do here is you're going to match up the cation from one with the anion from the other. So what's the cation from this compound?
Ag plus.
So that would match up with which element from here?
Cl.
And then what would be the other matchup?
NaNO3.
Good. Is this compound, can we assume that this will be soluble?
Yeah.
Because it's got both sodium and nitrate. If it had either of them, would ensure that this was soluble. So this will still be AQ, dissolved in water. Can we assume that this will be soluble?
No.
Because neither of these are things that are always soluble, so it actually turns out that this will precipitate out. It would be hard to know that for sure without looking up all the rules for solubility. But when you're given an equation like this, you should pretty much assume, I guess, that these elements are going to precipitate out, because otherwise the equation would be totally boring. If nothing was going to precipitate out, you would just have all ions on the left and all ions on the right. So we should just assume this is going to precipitate. Okay, so this is what we could call a precipitation type reaction. Let's see. So by the way, what's the charge on nitrate?
-1.
Right. What's the charge on sodium?
+1.
How do you know?
It's in the first column.
That's right, of the periodic table. What's the charge on chloride?
It's -1.
And how do you know?
Because it's, actually I just memorized it, but
How could you figure out that chloride has a -1 charge?
just by looking at the position in the periodic table.
Because it's in the next to last column, which means it wants to gain 1 electron to have a complete octet. Nitrate has to be memorized, though. That one wouldn't be easy to figure out. Okay, let's see. 1 second. Let's see if that helps us with this problem. Try number 4.
A coffee cup calorimeter having a heat capacity of 472 joules per degree Celsius is used to measure the heat evolved when the following aqueous solutions, both initially at 22.6 degrees, are mixed. 100 grams of a solution containing 6.62 grams of lead-2 nitrate and 100 grams of solution containing 6 grams of sodium iodide. Final temperature is 24.42 or 24.2 degrees Celsius. Assume that the specific heat of the mixture is the same as that of water. Write a balanced equation for the reaction that occurs. Okay, well, we have lead-2 nitrate, so that's PbNO3 in parentheses 2 plus NaI, and that'll go to NaNO3 plus PbI2, and I2 is solid, AQ, 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 2. So it'll be a 1 to 2 to 1 ratio where there's 1 in front of the lead nitrate. Then we can put a 2 in front of the sodium nitrate. Then we can put a 2.
You mean the sodium iodide or the sodium nitrate?
Sodium nitrate.
Oh, okay. Excuse me. That's right. All right.
Then we can put a 1 in front of the sodium iodide, and then we can put a 2 in front of the lead. Or no, then we can put a 2 in front of the sodium iodide, and then we can put a 1 in front of the lead iodide. So there's our balanced chemical reaction part A.
Okay. That seems good. So let's see. How did you know that we needed 2 nitrates here?
Because lead is in the well, I just memorized that there's it said lead 2, so it also is in the well, yeah, I actually just memorized that it needed 2 because it's lead 2, so.
Okay, yeah. Now, so the point is, it's really not based on memorization. They called it lead 2, which means that it has a positive 2 charge. Lead is in the transition metals, right? And the transition metals, you can't figure out the charges from the periodic table. For transition metals, you can't figure out the charges from the periodic table. That's why they told us the charge. Okay, good. And let's see, how did you know the iodide had a negative 1 charge? Probably because it was like chloride in the next to last column. So that's good. And I think you balanced the equation here. Everything matches up. What phase did you say the lead nitrate would be in?
Lead nitrate would be aqueous.
And the sodium iodide?
Sodium iodide would also be aqueous.
And the sodium nitrate?
Sodium nitrate would also be aqueous.
And the lead iodide?
Solid.
How did you know that the lead nitrate would be aqueous?
Because all nitrates are soluble.
That's right. All nitrates are soluble, so this will be dissolved in water. And all sodium compounds are soluble, and that tells us this. On the other hand, these could precipitate out, and I just told you to assume on this type of problem that if they can precipitate, they will, because otherwise the reaction wouldn't be interesting enough for them to ask you about it. Okay, I think you did a good job on that. So I think that's the right answer for the balanced equation. So now we have part B for the same problem.
Calculate the heat of evolution. So what they're looking for is Q, and we can assume that Q, so both the solutions were initially at 22.6, and the final temperature of the whole system was 24. We can assume that it's an exothermic reaction, therefore Q is going to be negative. So since they do give us the specific heat of water, we can, and also the heat capacity of the calorimeter, we can say that Q is equal to MC delta T plus capital C delta T. And to assume the specific heat of the mixture is the same as that of water, well, if it's, I guess then we can say that we have I guess, a total of 200 grams, since we have 100 grams of each. So Q is equal to 200 times 4.184 times delta T, which is 24.2 minus 22.6, plus 472 times 24.2 minus 22.6. So 200 times 4.184 times 1.6 change in temperature, 1338.88 plus 472 times 1.6, and that is equal to 755.2. And then add those two up. And you get 2094.08 joules. But I guess we made a mistake since it didn't match our prediction.
That's good that you're checking that.
So they're both initially and the final temperature, so 24. That would have to be a positive number.
Good. So it's good that you were thinking about that. And now you'd have to go back and figure out what your mistake is. To save time, I'll give you some help with that. What would be a good symbol for what this question is asking us?
Q.
That's right. But we've seen in some previous problems we have to be more careful. Are they asking us for Q of the calorimeter assembly or Q of the reaction?
Oh, Q of the reaction.
Would you predict that Q of the reaction is positive or negative?
Q of the reaction would be negative because the final temperature is greater than the initial.
That's right. So the reaction must be exothermic. That's good. Now, in this equation, when you set up this equation, do these formulas give us Q for the reaction or Q for the calorimeter assembly?
Oh, they give it to us for the calorimeter assembly.
Yeah, so what we should have said, this is the Q for the calorimeter assembly. What do I mean by the calorimeter assembly? I mean the solid calorimeter plus the solution. So this is the Q for the, I don't know what to call it, but it's the whole assembly. The assembly, calorimeter assembly. All right, so how do those distinctions help us? So you figured out that Q for the assembly is 2094.08 joules. Now what?
Well, since we know that Q reaction is equal to negative MC delta T plus C delta T, that would mean that it would probably just be negative 2094.08 joules.
Who's it?
On the Q for the reaction.
Oops. Okay, good. So is the calorimeter assembly absorbing or releasing heat?
It's absorbing it.
How much heat is it absorbing?
Positive 2094 joules.
Where is it getting that heat from?
The reaction.
So how much heat is the reaction releasing?
The same, but negative.
Right. Okay, good. When you were articulating that, I don't know if everything you were quite saying was quite right. It sounded like you were going back to the MC delta T and the C delta T, but we don't need to go back to those. We can just say, in general, what's the relationship between Q reaction and Q for the calorimeter? What's the general formula that relates Q for the reaction and Q for the calorimeter?
Q for the calorimeter is, Q for the reaction is equal to negative MC delta T, where Q for the assembly is equal to MC delta T.
Okay, now that's true sometimes, but we couldn't use that in this example because in this example, actually, we needed MC delta T and C delta T. So what you were just saying wouldn't be quite right. But let's just try to write an equation that only involves Q for the reaction and Q for the calorimeter assembly. What would be an equation that you could write that involves only Q for the reaction and Q for the calorimeter assembly?
Q for the reaction is equal to negative Q of the calorimeter.
That's right. I think we spent quite a bit of time in a previous session trying to satisfy ourselves of that. So if you just think about it in those terms, I think that's the simplest thing to do here. These equations here tell you the heat for the assembly. And that's fine, because once you know the heat for the assembly, you can just take the negative of that to find Q for the reaction. So I think you're basically seeing that correctly. I'm just saying, once you know Q for the assembly, when you want to find Q for the reaction, there's no need to go back to the basics and think about MC delta T and C delta T again. You can just take the negative of Q for the assembly. So did our answer turn out to match our prediction?
Yeah.
It did. So it's good that you were checking that. The reason why your answer didn't seem to be matching your prediction was because you weren't distinguishing between Q reaction and Q assembly. So that's an important thing to emphasize. So what was the answer to part B?
Negative 2094.08 joules.
Okay, good. So now one thing, how did you know in this problem that you needed to treat the water as a separate heat sink, separate from the solid portions? Well, this was the type of hard problem that I was trying to prepare you for in the last session. In this case, they gave us the heat capacity for the solid calorimeter, and they specifically talked about the heat capacity of the solution as well. So that was a strong clue that they wanted you to include both of those two terms separately. Unlike the previous problem only gave you the heat capacity, and they said that was for the whole assembly. I'm not sure whether you'd actually see a problem this hard in your course or not, but well, this is something that your instructor gave you to prepare, so I guess they want you to know how to do this. But remember, this is a pretty hard problem. Most of the problems you see, I think you're only going to use one of these two terms. You only need to use both of them if there's a strong clue in the problem, but that's what you need to do. Okay. Now I think we need part C. Try part C.
I can't see it. Oh. Calculate the delta H for the reaction per mole of lead-2 nitrate consumed under the condition of the experiment. Well, we know the total Q for the reaction is 2094.08 joules. It said delta H for the reaction per mole under conditions of the experiment. Well, we can take 6.62 grams of lead-2 nitrate and lead weighs 207. So let's see, that would be 16 times 6. And then 14 times 2 is 28 plus 207. And that's 331, so we can divide it by 331 grams per 1 mole. Grams cancel out. So 6.62 divided by 331. And that's 0.02 moles. So since Q for the reaction is negative 2094.08 joules per 1 mole, we can multiply this by 0.02 moles lead 2 nitrate. So 2094. And that is equal to 41.8816. So that is approximately equal to negative. Oh, and then they wanted the answer in. Okay, they didn't want the answer in kilojoules, so then that would mean that it's negative 41.8816 per mole of lead 2 nitrate consumed.
Is that your answer?
Yeah.
Well, tell me again, what was your answer?
Negative 41.8816.
And what are the units?
Joules per mole. Lead 2 nitrate.
And this was the calculation you did?
Yeah.
Is this what you wrote down?
Yeah.
What units did you write down here?
Moles of lead 2 nitrate. Oh, there is joules.
Like this? I can't see what you're writing down, so I just need to ask you. Is this what you wrote down?
Yeah.
And what units did you write down here?
Oh, below that, no units. Oh, there at the 0.02, it would be, moles. Oh wait, but the moles cancel out, don't they? Oh, well, actually, since I thought what Q for the reaction would be negative 2094.08 joules per 1 mole, and then
I see.
I multiplied it.
So let's go back to this. Why did you say that these were the units over here?
Because the units cancel out in the...
Well, what I meant is, why did you say that these were in joules per mole? Let's think about that for a second. So this was the Q for the reaction, right? The Q for the reaction, that means this actual reaction actually released 2094.08 joules, right?
Right.
Now, do you know that the reaction actually used 1 mole of starting material?
No.
So this can't be a correct interpretation. What you said was that this number was 2094.08 joules per mole. But that would be 2094.08 joules per 1 mole. That's not a correct interpretation because we don't know that there's actually 1 mole going through this. So when you look at this equation here, Q equals mc delta T, what are the units for Q in this equation?
Just joules.
Just joules, not joules per mole. You can see that because what are the units for M?
M is mass, grams.
And what are the units for little c?
Joules per gram degrees Celsius.
And for delta T?
Degrees Celsius.
Notice that you didn't mention any moles. There's no moles on the right-hand side of the equation, so the Q can't have anything to do with moles at all. So let's review that one more time. What are the units for Q in this equation?
Q is just joules.
Just joules. So what would be the units for this number that you got? Q for the reaction was negative 2094.08 what?
Joules.
Just joules, not joules per mole. It's true that sometimes we express the heat of a reaction in joules per mole, but this is not the appropriate number to use for that. This number was just in joules. All right, and then I think when you see that, you might need to change your approach down here. So if this number is in joules, how would you figure out the answer to part C?
Well, then I would just divide it by 0.02 moles lead to nitrate. And then negative 2094.08 joules divided by 0.02 moles is equal to negative 104,700 joules per mole of lead nitrate.
Tell me again what answer you got.
Negative 104,700 joules.
So what's the answer to the question?
Negative 104,704 joules per mole lead to nitrate.
Okay, so this number should also not have been joules. It should have been joules per mole. Of lead nitrate. Okay, so we had some problems with part C here. Now, you got off on the right foot because you saw that you needed to figure out how many moles of lead nitrate there were. So this was a good conversion to do. But then you weren't quite sure how to do that conversion. For one thing, so the mistake you were making is that you thought this number was in joules per mole. If this was already in joules per mole, then this would already be the answer. If this had already been in joules per mole, we already would have had the answer. Okay, I think we talked about this a little bit last time. You have to be careful when they're asking you for heat or energy, because the answer for a question about heat or energy could be in joules, or it could be in kilojoules, or it could be in joules per mole, or it could be in kilojoules per mole. So you have to try to read the problem carefully to see which of these units they're going for. Here they were pretty explicit that they wanted the joules per mole. And what's the symbol for this? What symbol did we figure out here? In part C?
In part C, it was joules per mole lead to nitrate.
Those are the units. What's the symbol for this concept that we figured out?
Delta H.
Right. Do you remember what delta H stands for? We talked about that last time. This is what's called the enthalpy change. And remember, the enthalpy change is the heat under constant pressure. Enthalpy change is heat under constant pressure. So why is it appropriate for them to ask for this here? Because notice this is a coffee cup calorimeter. I think we talked last time about how a coffee cup calorimeter is not sealed, so the atmosphere maintains the reaction at constant atmospheric pressure. So if we have a coffee cup calorimeter, the reaction is occurring at constant atmospheric pressure. Therefore, the heat will be the heat at constant pressure. So it's appropriate to call that the enthalpy. I guess you don't really need to think that through to get this right. You just have to say that they're asking us for the heat per mole. But that's why they asked you for the delta H here. Okay, how did we do on this then? I think, yeah, we had some trouble with this. We had problems with part B because we forgot to distinguish between Q reaction and Q assembly. And then we had some trouble with part C. And the main problem I think we had with part C was not putting the right units on this number. This was just in joules. So it would be good to go back and try this again. These problems are more subtle than I thought. All right, so let's take a look. One moment. Okay. Well, let's try number 5.
The combustion of 1.04 grams of benzene in a bomb calorimeter compartment surrounded by 955 grams of water. Raise the temperature of the water, the capacity for the calorimeter, write a balanced equation. Well, since it's a combustion, it'd be C6H6 liquid plus O2 goes to CO2 plus H2O. You can put a number 1 in front of C6H6 and put a number 6 in front of CO2. You can put a number 1 in front of the... no, maybe you shouldn't put a number 1 in front of the O2 yet, but we can put a number 3 in front of the H2O. 6, 6, 6, 6, 3. But now the oxygens aren't canceled out, or they're not balanced. So 12, 15. Put number 1 in front of C6H6. We can put number 6 in front of the O2 or CO2. Then we can put a number 1 in front of the oxygen on the right. But then this one's a little bit tricky.
Okay, I think we worked on balancing equations before, but it's been a while. I think you forgot one of the steps. So let's see here. I think the best advice for these problems, maybe we should start by putting in question marks for all the things we don't know. Now you started by saying there was one of these, which would require 6 carbons on the left, so we need 6 here on the right. Now we should leave oxygen for last. I think you saw that because oxygen appears the most often. So now we balance the hydrogens. There's 6 on the left, so this would be the number 3. So now how many oxygens do we have on the right? 15. But then there's no way to make 15 oxygens on the left with an integer coefficient. Now this is where you got stuck. I think you forgot the trick that we used when we went over this before. The trick is, if your first set of numbers won't give you integer coefficients, the trick is take all the original numbers and double them, and then try it that way. So now let's take all the original numbers and double them. So if we do that, what would be the coefficient for the C6H6?
So that'd be 2C6H6.
Now we're not going to double anything in front of the oxygen because we didn't assign it a number yet. And what's the coefficient here?
12. And then 6 for water.
Good. Now what?
12, 12, 12, 12, 24. That's 30. Now we can put a number 15 in front of the O2. And then we get 30 oxygens on both sides.
Okay, good. So when you were balancing this equation, you got off to the right start because you left the oxygens for last. The thing that was giving you trouble is that you saw that with your original coefficients, there was no way to balance the oxygen with integer coefficients. And then the trick that we needed to use here is, if your first set of coefficients doesn't work, then double all the original coefficients, and maybe that will work. What would have happened if doubling didn't work? Well, then we would go back and triple the original coefficients, and that would probably work. Okay, so this is the answer then to the question. Write a balanced equation for the combustion reaction. Well, this is well, All right, so this is one answer. Sometimes for a combustion reaction, they want you to have only 1 mole of the thing you're burning. So how would we write this to have only 1 mole? You'd have to take all these numbers and divide by 2. So that would give us one of these. And then if we're dividing everything by 2, how many moles of O2 would we have?
7.5.
Right, although it would probably be written like this. And then what numbers would we put here?
6 and 3.
Sometimes when they say the combustion reaction, usually combustion reactions are written with the number 1 in front of the hydrocarbon. So maybe this is what they're really going for. I don't know. But still, for most students, the easiest way to do this is to first get the equation with integers. And then, if necessary, you can reduce it down. Okay, so now let's try part B.
So now they're looking for delta E for a bond calorimeter in kilojoules per mole and kilojoules per gram. And since it's a combustion reaction and the final temperature is greater than the initial, then we can assume that it's going to be negative. So now, and this calculates delta E for benzene, so that means Q for the reaction is equal to MC delta T plus C delta T, where Q for the reaction is equal to the combustion of 1.048 grams well, since they didn't give us the specific heat of water, then maybe they don't want us to use it, so instead it would be Q reaction is equal only to C delta T, where capital C is equal to 891 times the change in temperature, which is 32.692 minus 23.640.
Okay, this is tricky. Let me give you a little help here. This actually contradicts a little bit what I told you in a previous problem. So the problem here is when they say that the heat capacity of the calorimeter is 891, do they mean that this is the heat capacity of the solid calorimeter, or do they, or just of the vessel, or do they mean this is the heat capacity of everything, including the water?
Just the solid part.
That's the tricky part. Why do you say that? It's hard to tell. Now, it's hard to tell here. What I told you before is if they don't give you the specific heat for the water, they probably don't want you to use it. But actually, I don't think that would work here. The thing I'm noticing here is, notice they told you how much water there was, right? There's a bomb calorimeter compartment surrounded by 945 grams of water. So what is this reaction absorbing or releasing heat?
It's releasing it.
And who's going to absorb the heat?
The water.
The water and the solid portions of the vessel. The solid calorimeter and the water together will absorb the heat. Here, I actually think they want you to treat the water separately from this. It must be just the solid portions, because otherwise there's no reason to tell you the number of grams of water. Notice that if you just do it this way, you're never going to use the 945 grams of water, if you see what I'm saying. So I think yeah, what you were saying?
In the previous example, they gave us 1,000 grams, and they still didn't want us to use it.
Actually, if you go back to our work, we did. in the previous problem, we did use MC delta T.
No, I'm talking about the one before this one.
Oh, okay. Number 3. Let's see. Yes. Oh. You're right. Maybe we did that one wrong. You don't have the answers to these, I guess.
You did not give them to us.
Grams of water. So for number 3, I told you to ignore the water because they said calorimeter assembly. I thought that meant the water too, but then why would they tell you how much water there is? That's a good point. So I don't know. I'm not really. Maybe you should ask your instructor before the test because I'm not sure what the right way is here. Now I'm confused. They did say that there's 1,000 grams of water. Did we use that when we did this problem? Wait,
no.
That was number 3. Yeah, so for that problem, we never used the 1,000 grams either. I thought that when they said assembly, they meant including the water, but maybe by assembly they only meant the solid portions. Again, I might have misinterpreted that. I'm not sure now. All right, so let's see. So the first problem we did here, they said the calorimeter assembly, including the water, has this heat capacity. So in this case, it was obvious what we had to do. In this case, we didn't do the water separately. And then the assembly was 4.8 kilojoules. Now, for number 3, notice that this heat capacity is actually a lot less than 4.8. So maybe we did number 3 wrong. Maybe for number 3, they wanted us to include the water. Maybe when they say assembly, they just mean the solid portions, unless they're more specific. I don't know. And then going on here to number 5, surrounded by 945, the heat capacity of the calorimeter. Let me take a look at the textbook here for a second. The calorimeter has a heat capacity of... Okay, I'm not sure, but I think here that they want you to do the water separately, and I have 2 reasons. First of all, they wouldn't have even mentioned the water, probably the mass, if you didn't need to use it. But also, otherwise, this heat capacity seems too low. This heat capacity is less than 1 kilojoule. But we know from number 3 that if you include the whole assembly, here was an example where the whole assembly, including the water, was 4 kilojoules. So my best guess here is they want you to include the water. It might be good to ask the instructor, though, because it's kind of a matter of how they phrase the question. Okay, so we can't be sure, but let's go back and try this again. So let's see, where were we? So anyway, where I'm coming down on this is, I think maybe we did number 3 wrong. Maybe on number 3 we should have included the water separately, now that I think about it. So let's do it that way here. So on number 5, let's include the water separately. I think that's what they want. You can double check that with the instructor. So let's include this term. So what would we plug in for this term?
So that would be 945 times 4.184 times 32.692 minus 23.640.
Okay, good.
So we take 891 times 9.052, and that is equal to 8,065. And since it's Q for the reaction, then that's going to equal negative C delta T negative MC delta Z, so that would be equal to negative 8,065 joules plus and then that's equal to a negative 35,790. So then we can add those two up and we get Q for the reaction is equal to the negative 43,855. 856 joules. And since they want our calorimetric data in kilojoules per mole and kilojoules per gram, if you can take this number and divide it by 1,000 joules per 1 kilojoule, and we'll get negative 43.85 kilojoules. Now I can take and then we can divide it by the number of grams of benzene, which in this case is 1.048 grams. And that is equal to 41.85. Negative 41.85 kilojoules per gram of benzene. And then also negative 43.85 kilojoules divided by, let's see, that's 66. It's 1.048 grams divided by 66 grams per 1 mole. That's equal to 0.0157 moles. So
let's go back to that calculation you did here. You did 1.048 grams, and what number did you write here?
Oh, sorry, 78.
Yeah. Because that's the molecular weight, 6 times 12 plus 6 times 1. Good.
So now it's 0.01343. So then negative negative 41.85 divided by 0.01343. Whoa, 41.85 divided by 0.01343. Wow. I get, and that is equal to negative 3,116 kilojoules per mole of benzene.
All right, I must have been rounded off differently than you. I got something a little different, but I think that's just rounding differences. Okay.
And those are my final answers. Negative 41. Actually, whoops, let me double check that really quickly. I got 41.85 grams per kilojoule, 41.85 kilojoules per gram, so then take 43.85 divided by 0.01343. So I got negative 3,265.
3,265?
Yeah, kilojoules per mole of benzene.
Okay, and what calculation did you do to get that?
I took negative 43.85 joules and I divided it by 0.01343 moles of benzene.
Okay, actually it looks like I made a mistake here. Yeah, so this should have been, where's my mistake? 44 kilojoules divided by... Alright, tell me one more time what your answer was.
Negative 3,265 kilojoules per mole of benzene. And negative 41.85 kilojoules per gram of benzene.
Alright, I still got a little bit different, but maybe now that's just from rounding error. So this was 44 kilojoules over 0.013 moles. And here we had 44 kilojoules over 1.04. 44 divided by 0.013. Okay, yeah, so that's about right. Okay, so going back to this equation here, what does MC delta T plus C delta T tell you? Does that tell you Q for the reaction or Q for the whole calorimeter deal?
Q for the reaction is equal to negative MC delta T plus C delta T, so that'll be BQ for the reaction.
The way I have it written down. So I guess if you were going to do Q for the reaction, you'd do negative MC delta T minus capital C delta T, right?
Right.
Okay, it sounded like you were putting in a plus here. I think, though, that the easiest way to do this is just to say this is the specific heat for the water and this is the heat capacitor for the calorimeter. So this gives us the Q for the apparatus plus water. This is the Q for the apparatus plus the water. And then when you want to find the Q for the reaction, that'll be the negative of that. I think the best thing to do in the equation is just to find the Q for the apparatus and the water and then take the negative of that for the reaction. But I guess you were thinking about this correctly because you came out with the right answer. All right, so like I said, maybe some of the things I was telling you before were not quite right for the problems you're going to see. Even though this didn't give you the specific heat for the water, I still think they meant you to calculate that separately because otherwise there's no point in telling you the mass of the water. And also, this number seems like it's too small to include the water. This number seems like it's too small to include the water. So I think they want us to include another term. So I guess we didn't do number 3 correctly before. You might want to go back and do it again. All right. Why did this? Notice that number 4 asked you for delta H, and number 5 asked you for delta E. That didn't really change how we solved the problem at all. But why did they ask you for different symbols? Well, remember that here we were using a coffee cup calorimeter, which occurs where the reaction occurs at constant pressure. So the heat is the enthalpy change, because that's the heat at constant pressure. But here we were using a bomb calorimeter. Bomb calorimeters have constant volume, not constant pressure. So it made sense that they didn't ask us for delta H. We can't figure out delta H directly here. All we know is just the energy change. That doesn't really make much difference to how you solve this. In both cases, you just had to use the heat. By the way, notice why did they have to use a bomb calorimeter here and not a coffee cup calorimeter? Well, you can't really do a combustion reaction in a coffee cup. You can't burn something in a coffee cup. The coffee cup calorimeter is just for reactions that take place in solution. All right, so let's move on then, and well, let's see. All right, this last problem here, this is a hard problem, but give it your best shot. Let's try number 6.
A 1.567 gram sample of naphthalene is completely combusted in a bomb calorimeter assembly, and a temperature increase is observed when well, they're looking for the heat of combustion of thymol, so they're looking for Q. And they're looking for it expressed in kilojoules per mole. There was a temperature increase. And I guess we can't really make a prediction since they're asking for the heat of combustion. However, they are looking for Q expressed in kilojoules per mole. And I guess both the naphthalene and the thymol were combusted at the same time, not separately. So since the heated combustion of thymol is that, and we're given the grams and the change in temperature, we're not given the specific heat. So I guess in this case Q so and they didn't give us the specific heat of the heat capacity for the calorimeter. Well, since the heat of combustion of naphthalene is 553.9 kilojoules, Then 553.9 Q is equal to
This is a hard problem, so let me give you some help with this. Now, first of all, we could have gotten a prediction. Think again about what would be a good prediction for this problem.
Q is going to be negative because it's being combusted.
That's right. Are they asking us for Q of the calorimeter or Q of the reaction?
Q of the reaction.
Right. Maybe we shouldn't call it Q, though, because we don't usually put Q in kilojoules per mole. But anyway, one of the things we can predict that the answer, they want, I don't know, I guess they're
Delta
basically
E.
asking for delta E. Yeah. Delta E of the reaction, and we can predict that that will be negative. All right. Now, notice that they're talking about combusting two different things. And you are asking yourself a good question. You are asking, are they combusting them at the same time or separately? Well, here's the clue. What was the temperature change when they combusted the naphthalene?
8.37 degrees Celsius.
Yeah. Whose temperature increased by 8.37?
The naphthalene.
Well, they don't, in these problems, they don't measure the substance directly. After all, remember, the naphthalene is all burnt up. The naphthalene
That's
is all
right.
burnt
It's
up.
the water.
Yeah, it's the water and the whole calorimeter assembly that's going up by 8.37. And then how about when they burned the thymol? What was the temperature change?
6.12.
So did they burn them separately or at the same time?
Separately.
Because otherwise they couldn't have different temperature changes, right? Different temperature changes means they're doing them separately. Now, which one is the question about?
The thymol.
So we should have said that. That's for the thymol. So let's just try to focus on the thymol and answer that question. So what would be a good equation to start with to try to analyze the thymol? What should be a good general equation to start down to try to analyze the thymol combustion?
Q equals MC delta T, where M is 1.22.
Sorry, let's do that together a little bit. Are you so Q? Now, one problem here is that they didn't give us specific heats or heat capacities. I guess I'll just give you a clue here and say it would be better to use this equation.
But they didn't give us the heat capacity of the calorimeter.
That's true. But nevertheless, we'll see why in a second. So is this Q for the calorimeter assembly or Q for the reaction that we're calculating in this equation?
Q for the reaction.
Well, no. If it was Q for the reaction, we'd have to put in a negative sign, right?
Oh, so then it's Q for the assembly.
It's Q for, the assembly plus the water, the whole thing. Assembly plus water. Okay. So is there anything we can plug in here? Can we plug something in for delta T?
Yeah, we can plug in 6.12 times capital C.
Because that was the thymol, which is what we're trying to figure out. Oh, so I should have specified what we're doing here is the thymol. So thymol. So for the thymol, the temperature increase would be 6.12. So it looks like we would be home free if we just knew C, right? Because Q is basically what we're trying to figure out. So if we just knew C, we'd be done. Does that make sense?
Yeah.
All right, but they didn't tell us capital C. However, they did do a whole other combustion. They also did the combustion of naphthalene. So there must be some way to figure out capital C from the combustion for naphthalene. This is a harder problem than the ones we've been doing before. Now we have to figure out capital C from the combustion for the naphthalene. So what would be the first equation to write down to analyze the combustion of the naphthalene?
Q naphthalene is equal to MC delta T.
Now I'm not going to write MC delta T because we decided to use this type of equation for analyzing this.
All right.
Okay. Now, let's see, plugging in here, what could we plug in for delta T?
So now we can plug in 8.37.
Because now we're doing the naphthalene, so that would be 8.37. So now we have two separate columns. Is the Q in this column going to be the same or different from the Q for the naphthalene?
It's going to be different.
Yeah, because they're two different things. You're going to get a different amount of heat from burning the naphthalene than for the thymol. So these are two different Qs. Is the capital C going to be the same or different in the two columns?
They're going to be different.
Now, that's tricky, but this is the capital C of who? This is
Oh,
who?
for the assembly, that's right. They'll be the same.
Because this is the capital C of the calorimeter. And the whole point here, so here's the clue. Did you notice they say it was burned in the same calorimeter assembly? That's the clue. The two combustions are done in the same calorimeter assembly, which means they both have the same capital C. So here's our plan. If we can figure out capital C in the right for the naphthalene, then we can plug that in over here. So this is a harder problem than the ones before. What we need then is we need to plug in a number for the Q for the naphthalene here. So can you figure out, how can we figure out what number to plug in for Q here for the naphthalene?
Well, they give us the heat of combustion, so I'd probably plug that in.
Okay.
The 5,153.9 kilojoules per mole.
So what would I write down here?
5,153.9 is equal to C.8 times 8.37.
What would be the units for this number?
Kilojoules per mole.
What are supposed to be the units for Q in this equation?
Kilojoules.
That means that there's a mistake there. I think we've seen that on some previous problems. You can't plug in kilojoules per mole for Q, because remember there's no moles on the right-hand side. So that was a mistake. We can't plug in 5,153.9 kilojoules per mole. We need to plug in the actual number of the actual amount of heat, not the kilojoules per mole. So how can we figure out what to put in here?
So since we know that 5,153.9 kilojoules per 1 mole of naphthalene, then we have to multiply, let's see, they give us 1.567 grams of naphthalene, and that's 128, so divide that by 128 grams per 1 mole. That is equal to 0.012 moles.
Okay, let me keep up with you here. So that's C10H8. C10H8, 128, right? So that's 1.567 divided by 128.012 moles. Okay, good. So now what?
So multiply that by 5,153.9, and I get 63.1 kilojoules.
5153.9 times 0.0122. What did you get again?
63.1 kilojoules.
Let's just call that 63. All right. Then what? Okay, now what?
Well, now since 63.1 is equal to capital C times 8.37, we can divide by 8.37, divide by 8.37. And then that means that the heat capacity for the calorimeter is equal to 7.54 kilojoules.
Okay, good. We'll just call that 7.5. Yeah, so what was capital C?
7.5 kilojoules.
Those units are not correct.
.5 kilojoules per degree Celsius, right?
Yeah, that's right. A second ago you just said kilojoules, but
Oh.
it should be kilojoules per degree Celsius. It's really important to be really careful with the units on these problems because that's been trapping us up. How do you know that this is in kilojoules? How do you know this came out in kilojoules and not joules?
Because we figured out the kilojoules.
Yeah, we plugged in kilojoules. Actually, if you look back, in most of these problems, the capital C, I think we've been using capital C's that were in regular joules. But here, as long as we're consistent, we can use kilojoules since we plugged in kilojoules. Okay, good. Now what?
Well, now since we know the heat capacity of the calorimeter, we can do the same for thymol, where Q for the assembly is equal to 7.54 kilojoules per degree Celsius times 6.12 degrees Celsius. Now Q for the assembly is equal to 46.14 kilojoules. So if that's Q for the assembly of thymol, then that means that Q for thymol, in other words, Q for the reaction, would actually have, Q for the reaction. Q for the reaction is equal to negative 46.14 kilojoules.
Good.
And since that's for the reaction, and they want it in kilojoules per mole of thymol, then we can take negative 46.14 kilojoules and then divide it by, let's see, 1.227 grams of thymol, and then thymol is 120, 134 plus 16 is 150 grams per 1 mole. That is equal to 0.00818 moles of T. So negative 46.14 kilojoules divided by 0.00818 moles of thymol. And that is equal to negative 5,641 kilojoules per mole of thymol, and that's the heat of combustion. So delta E for thymol is equal to negative 5,641 kilojoules per mole of thymol.
Does that match our prediction?
Yes.
Because it's negative. Okay, so that was a harder problem than the ones before. Notice how I organized my work here in 2 separate columns. I would recommend that would be a good way to do these so that we don't get them confused with each other. All right, so let's review the steps here. So we had to realize here that there was really 2 separate combustions happening. So we need 2 separate columns for the 2 combustions. How did I know to use C delta T and not MC delta T? Well, remember, this is what we would use if we were trying to think about, say, the water separately. How do I know that I shouldn't be treating the water separately in this case? Well, the main clue is they didn't give us the mass of the water. I think on this problem, at first, your instinct was to use MC delta T. But what we would do then is we'd use the specific heat of water and the mass for the water. Am I right? I don't think they mentioned the mass of the water here. No, they didn't tell you the mass of the water, so I think that that's so we're not going to treat the water here separately. Or anyway, the basic point here is from the naphthalene we can figure out the heat capacity of the entire calorimeter assembly plus water. From the naphthalene, we can figure out the heat capacity of the entire naphthalene assembly plus water, so there's no reason to do the water separately. That would be double counting. So the key here was to do a separate column here for the naphthalene and figure out this capital C. By the way, this problem might seem hard, but this is realistic. This is how, the basis of calorimetry in real life. Remember, the whole purpose of calorimetry is to figure out what the delta E or the delta H is for a reaction, but that only works if you already know the heat capacity for your calorimeter. So in real life, how do people figure out the heat capacity of their calorimeter? Well, the way to figure out the heat capacity of the calorimeter is to combust something where you already know the delta H or the delta E. So for example here, naphthalene, they already knew the heat of combustion of naphthalene. So when they combusted it, they were able to plug in and figure out the heat capacity of the calorimeter. And then they can use the calorimeter again now to figure out the delta E for reactions where they don't know the heat of combustion. Okay, so anyway, the way I organized this is how I'd recommend organizing this, with 2 columns for the 2 separate situations. I give you a couple minutes to try this on your own. This was a hard problem, so it's it's not surprising that you got stuck on this. But what should you? How do you figure stuff out in science? Remember that in these questions we always start by writing down a symbol for what the question's asking us. And then how do you figure out the answer? The way you figure something out, the way you answer a problem, is you try to write down an equation. You try to write down an equation and solve for the variable you need. Now, what should you do if you write down that equation and there's too many unknowns? That's what happened here. We wrote down this equation and there was too many unknowns because we didn't know capital C. Well, if you write down an equation and there's too many unknowns, this answer is try to write down another equation. That was the key step that you weren't taking. You took this step and you wrote down the equation, but then when you saw that there was an unknown, you didn't take the next step, which is to write down another equation. So that might be a good thing to have in your notes. That's the way to deal with hard problems in science. If the first equation isn't good enough, write down another equation, since this first equation ought to be enough to solve the problem. That's a good thing to keep in mind. Okay, and then I think we went through this. We answer this in the right units, heat of combustion. Okay, so let me give you this. That would be a good problem to try again, since that was a tough one. Okay, tell me when you have this copied down.
Okay.
All right, 1 second. Let's not get started just yet. It's combusted. 0.642 rise. 0.265 grams of caffeine. 25. Okay. All right. Now, actually, before we do that, there was something else I wanted to discuss with you from the last problem. So let's say that we have let me ask, let's say okay, what's the answer to this question?
We don't know what distance he drove.
So the answer is you can't tell?
Yeah.
So suppose someone said, oh, Bob drove 60 miles. Would they be right or wrong?
They would be wrong.
Okay, good. So you're right. In this case, we can't tell. A naive person might think that he drove 60 miles, but this doesn't say 60 miles. It says 60 miles per hour. That doesn't tell us what distance he actually drove. It just, is this number 60 here actual or hypothetical?
It's hypothetical.
This is the hypothetical distance he would drive if he hypothetically drove for 1 hour. But that's not the actual distance that he actually drove. So now what's the answer to this question?
A reaction has delta E. How much? Well, we don't know what kind of a reaction happened, but negative 10 kilojoules per mole.
So what's the answer to the question?
Actually, we don't know yet.
So what's the answer to the question?
We can't tell.
That's right. Now, if we were naive students, we would fixate on this number and we would say, oh, the answer is 10 kilojoules. But that's not right, right? Because is this number 10 a hypothetical heat or the actual heat?
Hypothetical.
It's just hypothetical. It's hypothetically how much heat would be released if we hypothetically combusted 1 mole. But I didn't tell you that we were combusting 1 mole. I didn't tell you how many moles we were combusting. So this is not enough information to figure out how much heat the reaction released. The problem is most students kind of think that kilojoules and kilojoules per mole are the same thing, but they're totally different. Just like 60 miles per hour is totally different from driving 60 miles. The per hour makes a huge difference. Kilojoules per mole is totally different than kilojoules. This is something we had trouble with on a bunch of the previous problems. I wanted to try to use some analogies to make this clearer, because this issue comes up a lot in lots of different places in chemistry, not just calorimetry. So, for example, if we were going to do Q for the calorimeter here, equals C delta T. So for this reaction that has a delta H of negative 10 kilojoules per mole, Let's say that it's done in a calorimeter, so we need to plug in a number for Q for the calorimeter. So for this reaction right here, what number would we plug in for Q for the calorimeter?
We would plug in negative 10 kilojoules per mole. Actually, no. No, we wouldn't, because we can't tell yet.
So what should we plug in for Q calorimeter?
Nothing.
Yeah, we can't tell yet. All right, so you almost fell into the trap, but you caught yourself. It was a trick question, because what are the units for Q calorimeter in this equation?
I'm sorry, say that again?
What are the units for Q calorimeter in this equation?
Just kilojoules.
Kilojoules or kilojoules per mole?
I'm sorry?
Should the units be kilojoules or kilojoules per mole?
Only kilojoules.
So this can't possibly be right. This is not the right number to plug in because this is kilojoules per mole. What we need to plug in here is the actual amount of heat that the calorimeter absorbed. Well, how much heat did this reaction actually release? How much heat did this reaction actually release? How much heat did this reaction actually release?
We can't tell yet.
Yeah, we can't tell yet. So how much heat did the calorimeter actually absorb?
We don't know.
We don't know. Okay, I'm making a big deal about this and giving you a bunch of trick questions because this is a trap that I think we fell into in a lot of the previous problems. And this comes up in a lot of places in chemistry, so it's important to try to get over this problem. Ratio units are different from non-ratio units. You can't just ignore the units on the bottom. Okay, so I'm going into this now because we had that problem on the last question. Going back to here, the problem that we just did, at first, when I asked you what you were going to plug in for Q here, at first you said you were going to plug in 5,153 for Q. But do you see that would be the mistake we're just talking about? Because this is not the actual heat, this is the hypothetical amount of heat that would be released if we hypothetically burned 1 mole. It would not the actual amount. That's a problem we've had in a bunch of these problems. So that would be an important thing to put in your notes. Q has to be the actual amount of heat in joules or kilojoules. It can't be the hypothetical amount of heat that comes from the kilojoules per mole or the joules per mole. So like for example, going back to these problems, so just like if you're driving 60 miles per hour, that doesn't tell you what distance you've actually driven. If the reaction is releasing 10 kilojoules per mole, that doesn't tell you how much heat it actually released. What extra information do we need to figure out the actual amount of heat here? What extra information?
Could you say that again?
What extra information would we need to be told to figure out the actual amount of heat that was released?
I couldn't hear you.
In this problem here, you were telling me that this is not enough information to figure out the actual amount of heat that was released. What extra information do we need to figure out the actual amount of heat that was released?
We would need the change in temperature.
I guess that would be maybe one approach, because then you could do that from the equation. But then you wouldn't really be using this number. What extra information do we need that we could use with this to figure out the actual amount of heat that was released?
We need the amount of the substance that's being reacted with.
Yeah. In what units?
Either
what
grams or
most,
moles.
Yeah. It would be most convenient to have it in moles. We need to know the actual number of moles. If we knew the number of moles, for example, suppose I tell you that there are 2 moles combusted, then how much heat was actually released? If there were 2 moles combusted, how much heat was released?
Negative 20.
Right, because 1 mole would be negative 10. If there were 3 moles combusted, how much heat would be released?
Negative 20.
Did you hear the question? If there were 3 moles combusted, how much heat would be released?
Negative 30.
Right. If there were 4 moles combusted, how much heat would be released?
If there are how many?
4 moles. Can you see my screen?
Yes.
Okay.
Yes. Negative 40.
All right. But if they don't tell you the number of moles, then you have no way of figuring out what the heat was. Just like over here, what extra information do you need to figure out what distance Bob drove?
You'd have to know his time.
Yeah, we need to know how many hours he was driving for. If you know how many hours he's driving for and you know the miles per hour, then you can figure out the distance. But you can't figure it out just from this. Okay. All right, so I was trying to make a big deal about that because that's giving us, we've had trouble with that in a lot of the previous problems, plugging in kilojoules per mole for Q when we should just be plugging in kilojoules. And like I say, that's an issue that comes up in a lot of different places in chemistry. So don't confuse ratio units with actual units. Don't confuse the hypothetical numbers with the actual numbers. I hope that made some sense. All right, so like I said, that was why in this problem we were not supposed to plug in 5,153 for Q. We had to multiply this by the number of moles, and then we plugged in 63 for Q. All right, now let's try this problem.
When a 0.235 gram sample of benzoic acid is combusted in a bomb calorimeter, a 1.642 degrees Celsius rise in temperature is observed. When a 0.265 gram sample of caffeine, C10H8 or C8H10O2N4 is burned, that rise in temperature using the value of heat of combustion of benzoic acid, calculate the heat of combustion per mole. Well, they're looking for a constant volume. They're looking for delta E for caffeine, and we can assume that it's negative because it's being combusted. And we can set up two equations, one for caffeine, one for benzoic acid, where we use Q for the assembly is equal to C delta T for both, since we have too many unknowns. And then we can use our given information where Q for the assembly is equal to C times 1.642 for benzoic acid, and Q is equal to C times 1.525 degrees Celsius for caffeine. And then then what we can do, since they gave us the heat of combustion for benzoic acid, we can plug that in for Q. So 26.38 kilojoules per gram is equal to C times 1.642, and then we can divide by 1.64. No, actually we can't divide yet because we need to get it in just kilojoules. So what we can do is we can multiply that number by 0.235 grams of benzoic acid, and then we'll get 6.2 kilojoules. 6.2 kilojoules is equal to capital C times 1.642 degrees Celsius. And then we divide by 1.642 degrees Celsius on both sides. And we get the specific heat for the calorimeter is equal to 3.776 kilojoules per degree Celsius. Now we can plug that in the other equation. Q for the assembly is equal to C delta T for caffeine, so Q is equal to 3.776 times 1.525. And since degrees Celsius cancel out, and we're left with kilojoules, so 3.776 times 1.525 is equal to 5.7584 kilojoules. And since they want it, I'm assuming they want it in kilojoules per mole, so they make it take our 0.265 grams of caffeine and then we can divide it by the atomic weight, which is 194, so 0.265 divided by 194 is equal to 0.001366.
Check that last calculation again. How did you get the 194? Oh, actually, maybe I made a mistake. Let's see. I forgot the nitrogen. All right, I'm wrong. You're right. 194. Good.
And then we get 0.001366 moles. And then we take 5.7584 kilojoules and we divide it by 0.001366 moles. And we'll get Q for the assembly, which is equal to 4,215 kilojoules per mole of caffeine.
What was that last number?
4,215 kilojoules per mole of caffeine for the assembly. And since they're asking it for the reaction, it'll be negative 4,215 kilojoules per mole of caffeine.
Okay. Good. So yeah, this was a positive number, but we want the Q. This was the Q for the assembly, so Q for the reaction will be the negative of that. So what's the answer to the question?
I'm sorry?
What's the answer to the question?
Negative 4,215 kilojoules per mole of caffeine.
Good. I got 217, but we must have rounded different. Okay. This is a pretty similar question to the one before. Once you see how to do it, it's a lot easier. So hopefully you were organized in your work here and organized this into two columns like this. Do these two columns have the same Q or different Qs?
They have different Qs because they're dealing with different substances.
Yeah, we're burning different things, so there'll be different amounts of heat. And do they have the same delta T or different delta Ts?
They have different delta T's because that's given to us.
Yeah, those are two different experiments. Do they have the same capital C or different capital C's?
They have the same capital C.
Yeah, how do you know?
Because we figured it out. And because we're using the same calorimeter.
That's right. They weren't quite as explicit about this as in the previous problem, but we're assuming that we're using the same calorimeter in both cases, while capital C is just a physical characteristic of our calorimeter. So that's the key to this problem, that the capital C is going to be the same in both of them. That's always important when you set up two separate columns, to make sure you know which variables are the same and which are different in the two columns. Now, we were teetering on the brink of disaster here. For a second, it sounded like you were going to plug in the 26.38 for Q. At first, it looked like you were going to plug in the 26.38 for Q, but fortunately, you caught that mistake. That was the issue that we were talking about right before this problem. Why is it wrong to plug in the 26.38? Well, one way to see that is it's got the wrong units. This is in kilojoules per gram, but what are the right units for Q?
Joules or kilojoules.
Yeah, you can't have per gram. So it's good that you caught that, and then you realized that you had to do a conversion here to figure that out. This 26.38 number, is the 26.38 an actual amount of heat or a hypothetical amount of heat?
It's the hypothetical amount of heat.
That's right. It's the hypothetical amount of heat that would be released if we hypothetically burned 1 gram of benzoic acid. But did we actually burn 1 gram of benzoic acid?
No.
No, we actually burned 0.235 grams. Well, what number do we need to plug in here? We need to plug in the actual amount of heat. So it's not this number, it's this number. This is the actual amount of heat that was actually released. Okay, so it's good that you caught that mistake, but it looked like we were on the brink of doing that, so that's an important thing to highlight. You really want to review that before the exam to make sure that you don't fall into that trap. I guess that's very tempting on these problems. Otherwise, it seemed like this problem went pretty smoothly for you. You did all the conversions, calculate the delta for this. Okay. Okay. So we spent quite a bit of time going over those calorimetry problems. So now it would be good for you to go back and redo a bunch of those calorimetry problems. Since we put a lot of time into that, you want to make sure you're going to get those right if you see them on the test. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you.